All right. So as an example of the stuff that we learned in the last two lectures, I would like to briefly talk to you about forced oscillations. Okay. And then I will only deal with the case where there is no damping. I can do this problem with damping also using the same techniques that I've developed, but just for simplicity's sake, I will just keep damping to 0 for now on, which means that my left-hand side of my ODE is obviously my double dot plus ky, where c is equal to 0. The damping coefficient I've set to 0. Okay. Now, if this is an undamped oscillator, obviously it's a sort of a fictitious case, right? Because the motion just keeps oscillating all the time. But now I'm not satisfied with that oscillation, so I'm driving this with a secondary oscillating force. Okay. Now the right hand side doesn't have to be an oscillating force. It could be any force, but I'm choosing an oscillating force because this is applicable in many practical scenarios. Okay. Now I'm going to make an assumption to start with. There is a natural frequency of oscillation of the system, right? If I set the right hand side to 0, the homogeneous equation is my double dot plus ky equals 0, which, as you know, can be written as y double dot plus omega square y equal to 0, where omega, which is square root of k over m, is the natural frequency. So I'm going to distinguish the natural frequency of the system omega 0 from the driving frequency omega. Okay, I can drive the system with its natural frequency, and if I do, something interesting happens, as you probably already know. But right now I'm choosing these two frequencies to be distinct. Okay. So now let me rewrite this. Of course, you know the solution to the inhomogeneous equation. I will not insult your intelligence by trying to derive this. Okay. So now with this knowledge, we will go back and figure out the solution to the inhomogeneous equation. So let me write the inhomogeneous equation as y double prime plus omega 0 y. I'm dividing through by a factor of m. So the right hand side becomes f0 over m cosine omega t. Okay. All right. So since the right hand side is distinct from cosine omega 0, I could guess that my particular solution is of the form C1 cosine omega t plus C2 sine omega t. Okay. Now I'm also going to turn this into an initial value problem, and I'm going to tell you that I'm going to solve this oscillator subject to the condition that y at time t equal to 0 is 0, and the velocity at time t equal to 0 is also 0. Okay. I could certainly give it an initial kick and have a non-zero velocity, but this will make my equation sort of tractable. So how do I fix C1 and C2? Again, you fix C1 and C2 not by initial value conditions, because this is the on-sorts for the particular solution. You fix it by demanding that YP solves the equation. Okay. So plug this YP back in the original equation. But since this is still cosines and sines, you know that YP double prime has to be equal to minus omega square YP. Okay. Why? Because YP prime is going to make the cosine sine and sine cosine, and YP double prime is going to switch it back again to cosine and sine with a minus omega square out front. This is the characteristic of cosine and sine solutions anyway. So what does my equation look like? My equation is y double prime, YP double prime plus omega 0 YP equals f0 over m cosine omega t, and my on-sorts for YP is C1 cosine omega t plus C2 sine omega t, and if I plug this in, I get YP double prime would be minus omega square YP plus omega 0 square YP equals f0 over m cosine omega t. Okay, which means omega 0 square minus omega square times C1 cosine omega t plus C2 sine omega t equals f0 over m cosine omega t. Okay, so now equate the coefficients of cosine and sine on both sides, and you're going to fix the constants this way. Okay, so this tells us that C2 is obviously 0 because there is no sine on the right hand side. And C1, if I equate the coefficients of cosine omega t, I get f0 over m omega 0 square minus omega square. Okay. So this is how the method of undetermined coefficients fixes my particular solution. So now I can write the general solution as the solution to the homogeneous equation plus this particular solution. The solution to the homogeneous equation is obviously a cosine instead of sine. So a cosine omega 0 t plus b sine omega 0 t. Remember, don't confuse your omega zeros and omegas. The homogeneous equation only has omega 0 because there is no driving force. Plus c1 cosine omega t. So I would have this. Okay. Now that you have figured out the final solution, now impose the initial condition. So now I will demand that y of 0 is 0. What would this give me? This would tell me, well, the sine part would vanish because sine 0 is already 0. So I will have a plus f0 over m omega 0 square minus omega square would be equal to 0. Okay. Of course, if I had a non-zero position, I will have a non-zero right-hand side, but I'm starting with 0 position. So this fixes one of my constants, minus f0 over m. The other constant, of course, is fixed by the other initial value conditions. So y prime of t would be equal to minus omega 0a sine plus omega 0b cosine minus omega sine omega. Okay. So obviously, excuse me, y prime at 0 equal to 0 simply tells you that the coefficient b has to be 0. Okay. Because the sign obviously vanishes already. So this tells you that omega 0b is 0. Omega 0 is obviously non-zero. I know that the oscillator is oscillating. So which means that my coefficient b has to be equal to 0. So these initial values fix a particular solution for me. And I can write y of t as minus f0 over m cosine omega 0 t plus f0 over m cosine omega t. Okay. So the first part is the homogeneous part. The second part is the inhomogeneous, the particular solution. So y of t, of course, I can clean this up easily. Okay. So if I did not have any damping, and if I choose to drive my simple harmonic oscillator with an external sinusoidal driving force, this is what my solution would look like, subject to the initial conditions. The object is starting from rest at the point y equals 0. Okay. So up till this point is fairly mechanical. You can just follow your nose and then get the solution. What becomes interesting is, you should always check if the solution that we have, if you're actually investigating a physical system instead of just looking at an equation, if there is a story behind the equation, if there is a physical system, you should always check for plausibility of your answer. So what happens if omega goes to 0? If I take omega equals 0, does your equation make sense? Well, in that case, your y becomes f0 over m omega 0 square times 1 minus cosine omega 0 t. I want you guys to think about, that t came out weird. I want you guys to think about whether this solution makes sense. Okay. So there is one way in which you can easily check this. So you can go back to your original equation and put omega equal to 0 right here. What happens if I put omega equal to 0 right here? The right-hand side simply becomes a constant. Can you quickly tell me what the particular solution would be if the right-hand side is just a constant for this equation? We discussed this in class yesterday. Anybody? So I have the equation y double prime plus omega 0 y equals f0 over m. In this case, what is YP? I'm trying to motivate this factor of F0 over M omega square, omega 0 square. Okay, so let's go back to an example I think we worked out yesterday. There, example 1. We looked at this equation. And I told you that if the right-hand side is a constant, you could simply guess the particular solution. The particular solution is also a constant. Right? In this case, it was 5/3 because if you plug in y equals 5/3, it easily solves this equation. Right? So I also discussed the general case. So I'll apply this idea. And if you have a constant, obviously you can easily guess that the particular solution in this case would be F0 over M omega 0 square. Okay, plug this in. The omega 0 square is obviously cancelled, and y double prime is obviously 0 because y is a constant, and you get F0 over M equals F0 over M. So this certainly solves the equation. Okay, so this equation that you have here can be understood as a constant piece plus a cosine omega 0 t piece. The cosine omega 0 t piece can be understood because that is the homogeneous solution. So if I plug in all the initial conditions, only my cosine omega 0 is going to survive, which you can easily check. So this is the homogeneous solution. The constant solution is simply because in this case, you can easily check that the particular solution is a constant. Okay, so this is a fairly easy check that you can do. And a rather non-trivial check you can also do is what happens if I'm driving the system with the same frequency as its natural frequency. I cannot simply plug omega 0 equals omega in this equation because everything blows up. So the oscillations blow up. Of course, I also have a 0 over zeros form. So you know how to take the limits in these cases properly. So if you take the limit, omega goes to omega 0 of y of t, you get limit omega goes to omega 0. You can use any of your rules. You basically differentiate the numerator and the denominator and then take the limit, right? So in this case, you get, remember that you have to differentiate with respect to the parameter. In this case, the parameter is omega, not with respect to time. So this would be minus t f0 sine omega t. That will be the differential of the numerator. Omega 0 is, of course, a constant. It has nothing to do with omega, divided by minus 2m omega. And this gives you f0t over 2m omega 0 sine omega 0 t. Okay. So this leads to the situation where you have probably learned in your high school called resonance, where you're driving the system with the same frequency as the natural frequency of the system. And there is also an associated condition of beats that you can easily understand by plotting this solution. And the solution would look like, something like this. Okay. So there'll be basically two different kinds of vibrations, but the envelope of these vibrations is what is called beats, which is what you hear in musical instruments. Okay, so this is also slightly reminiscent of what you learned in your PH 101 as group velocity and phase velocity. If you want to make a connection between the quantum mechanical notion of momentum and the classical notion of velocity, you find that it is off by a factor of 2. And to make this connection, you discovered in your last semester that you're using the wrong notion of velocity when it comes to waves. You should actually use what is called the group velocity and not the phase velocity. So whenever you see these envelopes within which there is a bunch of smaller waves going around, you can always think of, you can always make that connection if you so wish. Anyway, so this is all part of the 2 sections in your book, which I encourage you to read. And the only reason I went through this is because I wanted to sort of give you a brief overview of how this is useful in practical cases, since we're not going to be used during the tutorial problems. Okay, So now I'm going to shift gears slightly. So we discussed one methodology to find the particular solution. And this methodology of undetermined coefficients is applicable in those cases where you have simple enough right-hand sides, right? So we started with y double prime plus p of x y prime plus q of x y equals some r of x. And we said that at this point, we are not going to talk about p of x and q of x, and we're just going to treat the left-hand side as a differential equation with constant coefficients, but we're going to switch on the r of x. And we claim that if r of x is simple enough, like a function whose derivative also looks like the function itself, right? So a combination of sine and cosine does that, exponential functions does that. And in these simple cases, we had a bunch of rules basically, which you can easily motivate by doing out the entire problem. And using these rules, we can figure out the particular solutions. Now, what happens if the right-hand side is, not so willing, and it's a slightly more complicated function, right? A log x whose derivative is 1 over x, has nothing to do with log x, or e to the some log x, or not e to the log x, e to the, for example, tangent x, or e to the sine x, or whatever it is. In those cases, of course, you would have to again try and figure out some way of doing this out. And there is actually a method that can be applied in the case where this r of x is not of the simple forms that we discussed. And this method that we're going to discuss goes by the name of method of variation of parameters. Okay, I'll quickly tell you what this means. And this is not at all difficult to understand, given you have done something slightly similar before. Okay, so what is variation of parameters and what it is that I'm going to vary? Okay. So remember a few lectures ago when we discussed the solutions of homogeneous equations, we discussed a very nice case where if you by some chance know one solution, you can basically figure out the other solution, right? So how did we do this? We said that if you knew one solution y1, right, knowing that y1 satisfies the differential equation, you can construct the other solution as some multiple of y1. Of course, not a constant multiple. That will mean that y2 is not linearly independent of y1. Some non-trivial function, and you can always write it this way. You can always write the second solution this way, and given a non-trivial u of x, you'll be guaranteed that y2 and y1 are non-trivially related and are not just linearly dependent on each other. And you plug this onsorts back into the equation, use the fact that y1 is actually a solution of the differential equation, and you were able to turn this differential equation of u into something that doesn't have the u piece, right? It only had the u double prime piece and the u prime piece. And then you basically said that this is a first order differential equation for u prime, and then you can simply integrate this and figure out u. Okay, so this is the rough series of steps that we followed in that particular example. We're going to do something not identical, but sort of similar. So here's what we're going to say. So you have, so let us say that you start with the differential equation p of x y prime plus q of x y equals r of x. And again, we are going to deal with only constant coefficients. So p of x is some a and q of x is some b. But r of x is not a simple function. If it's a simple function, of course, you can use the undetermined coefficient. So you're going to again start with the homogeneous equation. So you know that the homogeneous equation, the solution to this can be always written as c1y1 plus c2y2, where y1 and y2 are the basis, linearly independent functions. Okay, so variation of parameters is basically saying that maybe you can just tweak this solution and figure out a particular solution from this solution. Just as you said that the second solution is some function times the first solution in the case where you knew only one of the two linearly independent solutions. In this case, since I don't know the particular solution for the homogeneous case, I'm going to say that the particular solution can be written as I will take something similar, right? Just as I wrote the second solution as u times y1, I'm going to write the particular solution as something times y1 plus something times y2. But these somethings are not constants, because if they are constants, that is exactly my homogeneous equation, homogeneous solution. So I'm going to take the particular solution as some u of x times y1 plus some v of x times y2. Okay. And I'm going to figure out u of x and v of x. If I figure out u of x and v of x, and if I satisfy myself that this satisfies the inhomogeneous differential equation, I'm done. Okay. So I don't need any further justifications that this method works. But there is a problem at the outset. The problem is this. How am I going to fix u and v? Okay. Well, I need two conditions on u and v to fix u and v, because I have basically two unknown functions. I always have one condition. Basically, I can demand that yp satisfies this equation. Okay, that is going to give me one condition on u and v. Okay, so basically, I'll have to invent another condition and hope that my invention is okay and that it does indeed give me a proper solution. Okay, so this is the problem. So the onsorts in this case is that I'm going to try and solve this equation by claiming that I'm going to write something that looks like a homogeneous solution, but it is not, because the coefficients are not constants. Okay, so since the coefficients are not constants, it cannot be easily gotten by just knowing YH. So I'll have to figure out u and v. The problem with determining u and v is that I only know one condition on u and v. That condition is that yp satisfies the differential equation. So I'm going to have to figure out some other condition, which I will do. I'm going to figure out another condition by basically choosing a condition that makes my life simple. What do I mean? Well, let us go ahead and just blindly do out the problem. So what is yp prime? Since u and v are functions of x, I will have u prime y1 plus v prime y2 plus u y1 prime plus v y2 prime. Okay, so I'm suppressing the function on x because it's just cumbersome to write down every time. Okay, so this is slightly long but fairly tractable. But the problem is that if I take the second derivative again, I'm going to get too many different types of terms. Okay, so at the outset, I'm going to demand a condition saying that I'm going to demand that u prime y1 plus v prime y2 equals 0. Okay, how am I justified in doing this? Well, I will give you two justifications, neither of which will be particularly satisfactory, but that doesn't really matter, because as long as I have a solution, I'm golden. The first condition is that, look, u and v are completely arbitrary, right? Apart from the demand that they satisfy the differential equation. So supposing if u and v satisfy this condition, the second condition that I just pulled out of my hat, then I will have two conditions and I can fix u and v. So this will certainly solve my problem. Okay. Second, it will actually make my problem much easier to solve. Why would it make it easier to solve? Simply because my yp prime would now only have two terms instead of four terms. So the question is, would this be correct? Well, answers to that question have to be reserved till the end, because if it does give you a solution, if this procedure does give you a solution that is distinct from the homogeneous equation and which obviously solves the inhomogeneous differential equation, then that is all you really want. You want the particular solution. Okay, so let us reserve the judgment as to whether this is correct for later and simply follow this hint and keep going. So I will simply take this as a condition. I'll call this condition A, which I am basically imposing on the system. Okay, so now with this condition, my yp prime simply becomes u y1 prime plus v y2 prime. Okay, remember again that y1 and y2 are the solutions of the homogeneous differential equation. So what is yp double prime? Well, it is slightly less beastly in this case, because I'll have u y1 double prime plus v y2 double prime plus u prime y1 prime plus v prime y2 prime. Okay, Now I cannot go ahead and set this also to equal to 0 and only have these, because now my system will become overdetermined. Okay, so that will become a trivial solution. So let us have these two conditions, and basically the second condition is what we will quickly derive. I'll demand that this onsorts for yp solves the differential equation, and then I'll figure out the solution. Okay, so let's plug everything back in the original differential equation. So my second condition is that yp double prime plus p of x yp prime plus q of x yp solves the inhomogeneous differential equation. So plug everything back. Yp double prime would be u y1 double prime plus v y2 double prime plus this plus this. Okay, so that is yp double prime plus p of x. Yp prime is this guy, u y1 prime plus v y2 prime plus q of x. Yp, of course, is just u y1 plus v y2. And I want all this to be equal to the inhomogeneous term r of x. Any questions or any concerns at this point? So this is nothing mathematically deep. I'm simply plugging in my onsorts into the parent differential equation and demanding that this onsorts solves this equation. Okay, so this will give me a condition on u and v such that this onsorts is a solution. So let us collect terms with u and v. So if I collect terms with u, this gives me a y1 double prime. This gives me a p times y1 prime. And this gives me a q times y1. And you already see why this could become simpler. Similarly, if I collect terms of with v, I will get y2 double prime, y2 prime, y2. Okay, so I've taken care of most of the terms. What remains is basically first derivatives of u and v. Okay, so plus u prime y1 prime plus v prime y2 prime. And this whole thing has to be equal to r of x. Okay. But since y1 and y2 solve the inhomogeneous equation, what is the inhomogeneous equation? Sorry, homogeneous equation. The homogeneous equation is y double prime plus p of x y prime plus q of x y equal to 0, right? So this is 0 and this is 0 because y1 and y2 solve the homogeneous equation by assumption. Okay, so the demand that this onsorts solves the differential equation boils down to a fairly simple equation: u prime y1 prime plus v prime y2 prime equals r of x. And I'm going to call this equation b. Okay, and now the things become fairly straightforward because I have two equations and two functions to determine from these equations. So I will write a also underneath this. A is u prime y1 plus v prime y2 equals 0. This was a. So how do I solve it? Well, I'll multiply the first equation by y2 and the second equation by y2 prime, and I will subtract. Okay, so b times y2 minus a times y2 prime. This would become u prime multiplying b by y2 will give me y1 prime y2. Okay, and if I multiply b by y2 and a by y2 prime and subtract, the v prime pieces will cancel, as you can easily guess, minus y1 y2 prime equals, I'm multiplying b by y2, so r of x times y2. And what is this guy? Anybody?
Wronskian.
That's just the Wronskian. Very nice, right? So this is actually the negative of the Wronskian, if I'm right, right? Your Wronskian would be y1, y2, y1 prime, y2 prime. So this will be y1, y2 prime minus y2, y1 prime. So this will be minus w of y1, y2. Okay. So since I know that y1 and y2 are linearly independent, I'm guaranteed that the Wronskian is not 0. So I can divide by the Wronskian on both sides. So u prime would be equal to minus r of x y2 divided by w. Okay. And this gives me a very simple way to determine this unknown function u. So u of x would simply be minus integral r of x y2 divided by w times dx. Okay. And if I multiplied b by let us say y1 and a by y1 prime and subtracted, I would be able to get v. So v of x would be equal to r of x y1 divided by w dx. Okay. So now I have, so with these ways of determining the functions u and v, my problem is now solved. By construction, I have gotten a particular solution. And my particular solution in this case would be u times y1, was it? Yeah, u times y1. So which means this is my u. So minus y1 times the integral r of x y2 divided by w dx plus v times y2, so r of x y1 over w dx. Okay. So if my r of x is not a very simple function like sine or cosine or something like that, this is another way in which you can, in principle, get the particular solution. Now, if r of x is extremely complex, you might just have to leave this as an integral. But in this, if in cases where r times y2 over w is integrable, you will have a closed form expression for your particular solution. Okay, so this is another tool in your toolbox with which you can determine particular solutions in cases where you cannot apply the method of undetermined coefficients. But I want to stress that method of undetermined coefficients is easier than this method. Okay, so as long as you only have exponentials and sines, you have a specific set of rules to follow, and the only complication there is to figure out what the constant is for the yp, but that you can always figure out by demanding that your ansatz for yp satisfies the differential equation. Of course, where this is not applicable, you can move on to some specialized tricks, and this one of the tricks is called the method of variation of parameters, where we start with the homogeneous solution and then basically tweak the coefficients and claim that they are now some functions. Okay, so as long as yp is arbitrary, this is also arbitrary because u and v are arbitrary, so this is certainly valid to do. But mathematically, this is slightly easier because y1 and y2 are solutions of the homogeneous differential equation. Along the way, you impose another constraint on u and v, and with these two constraints, you can determine the particular solution effectively. Okay. Now you might worry about which one you choose as y1 and which one you choose as y2. Okay, so let us actually look at a very simple example. And I will violate the rule that I just talked about and give you an example where it's actually easy to do by inspection. So y double prime plus y is let us say sine x. Okay. Now again, if you are given this question in an exam, you should always choose undetermined coefficients, because undetermined coefficients, assuming you guys are experts by now, what will be the particular solution ansatz for undetermined coefficients in this case? So note that my homogeneous equation has the solutions y1, y2 is sin x and cos x, right? The right hand side is also a sin x, which means this corresponds to the case where the right hand side is already a function of the homogeneous equation. So my yp cannot be a sin x plus b cos x. Okay, it cannot be this because my homogeneous solution already contains a sin x. I don't want to repeat the same root, so I'll have to multiply this by an x. Okay. Anyway, so then you can plug this back in the equation and figure out what. So I'll figure out what A and B are, which we will not do because we have done enough examples. So it's certainly easier that way. But I want to illustrate this using the variation of parameters. Now, as I told you, you might worry about which one you call y1 and which one you call y2. So suppose if I say y1, y2 is sin x and cos x, right? And you basically just plug in y1 and y2 in this equation and solve for the particular solution. Okay, and then you might claim that, look, if my friend says y1 is cosine x and y2 is sin x, and this will give you a different answer. The question is, would it? So if you stare at this particular solution, do you think it is symmetric under the exchange y1 goes to y2 and y2 goes to y1? On the face of it, it doesn't look like it is symmetric, right? Because if I say y1 goes to y2 and y2 goes to y1, my yp has, the first term has a y2 with a negative y2, and the second has a positive y1, and this guy has a y1 inside the integral, and the second guy has a y2 inside the integral. And that doesn't look like the initial solution, but you should remember that under the exchange y1 to y2, the Wronskian also changes sign. Okay, so I'll actually demonstrate this explicitly. So y1 goes to y2, yp will become minus y2 integral r of x. R of x remains the same, but now y2 becomes y1. Now Wronskian is y1 y2 prime minus y2 y1 prime. And if I make y1 to y2 and y2 to y1, w goes to minus w, right? So this becomes a minus w plus y1, y2 becomes a y1, r of x, y2 divided by minus w dx. Put everything together, your yp becomes y2 integral r of x y1 w minus y1 r of x y2 w dx, which is exactly what you had initially. Okay, so under this exchange, everything remains the same, and that is a good thing, because otherwise it cannot really depend on which one I call y1 and which one I call y2. Yes, please.
Sir, if they weren't symmetric, then how should we proceed? Like, is there any?
No, I'm claiming that by construction they are indeed symmetric.
Okay.
So
Yeah,
if you take this formula for yp, this formula for yp is symmetric under the exchange y1 to y2.
Yeah. Okay.
It cannot be any other way. So now, the rest is very simple, right? So for this case, I'll take y1 as sin x. So for example, r of x in this case, excuse me, r of x in this case is of course sin x. So my particular solution in this case would be minus sin x, and the Wronskian of sin and cos is 1 integral, and the Wronskian of course sin omega x and cos omega x is of course omega. So this is something useful to remember. Sin x, this would be sin x cos x dx, okay, plus y2. What is y2? Cos x times integral r of x y1. So sin square x dx. Okay, and these are both fairly simple integrations that you can easily do and figure out. Okay, so this gives you the particular solution. Again, this is a simple example where you could have simply used undetermined coefficients, but I just wanted to illustrate that if you follow this procedure, you will again have an equivalent way of determining yp. Okay, so we'll stop here at this point, and tomorrow we will continue with a slightly different subject.
No, sir.